The multiplication factor for an energy meter connected to a current transformer, or CT, can be determined from the CT ratio. The multiplication factor represents the scaling applied to the current measurement to reflect the actual current flowing in the primary circuit. To calculate the multiplication factor, divide the primary current of the CT by the secondary current of the CT. In the situation where the CT ratio is 400 to 5, the primary current is 400 amps and the secondary current is 5 amps. The multiplication factor is calculated as follows: multiplication factor equals primary current divided by secondary current, which equals 400 amps divided by 5 amps, which results in a multiplication factor of 80. This implies that the energy meter displays a current reading that is 80 times greater than the actual current flowing through the primary side of the CT. For instance, if the actual primary current is 100 amps, the energy meter would indicate 8000 amps. It is crucial to understand the implications of the multiplication factor for accurate energy measurement and billing. While the CT ratio provides a basis for determining the multiplication factor, it is important to acknowledge that the meter's internal circuitry can also influence this factor. The manufacturer's documentation will offer specific details about the meter's configuration and any adjustments that might be necessary. Therefore, consulting the meter's manufacturer is highly recommended to obtain the most precise multiplication factor for the energy meter. When installing or working with energy meters and current transformers, several additional considerations should be taken into account. Firstly, ensure that the current transformer is properly sized for the expected current range in the primary circuit. Selecting a CT with an appropriate burden rating is crucial for accurate measurement and to prevent saturation, which can lead to distorted readings. Secondly, verify the polarity markings on both the CT and the energy meter to ensure correct wiring. Incorrect polarity can result in inaccurate readings or even damage to the equipment. Thirdly, regularly inspect the CT and meter connections for any signs of corrosion or loose wiring. These issues can introduce errors in the current measurement. Fourthly, be aware of the potential for harmonics in the electrical system. Harmonics can affect the accuracy of energy measurements, especially with certain types of meters. Consider using true root mean square, or RMS, meters that are designed to accurately measure current and voltage in the presence of harmonics. Fifthly, document all relevant information about the CT and energy meter, including the manufacturer, model number, serial number, CT ratio, and multiplication factor. This information will be valuable for future reference, maintenance, and troubleshooting. Sixthly, if the energy meter has configurable settings, carefully review the settings and ensure they are appropriate for the application. This may include settings for the CT ratio, pulse output, and communication protocols. Seventhly, consider using a calibrated test source to periodically verify the accuracy of the energy meter. This will help identify any drift or errors that may develop over time. Eighthly, adhere to all applicable safety regulations and guidelines when working with electrical equipment. This includes wearing appropriate personal protective equipment, or PPE, such as gloves and eye protection, and following lockout-tagout procedures when working on de-energized circuits. Ninthly, ensure that the energy meter is properly grounded to prevent electrical shock hazards and to minimize the effects of electrical noise. Tenthly, provide adequate ventilation for the energy meter and CT to prevent overheating. Overheating can affect the accuracy and reliability of the equipment. The NEC, or National Electrical Code, provides guidance on the installation and wiring of current transformers and energy meters. Refer to the relevant articles in the NEC, such as Article 310.15 for conductor ampacity and Article 450 for transformers, for specific requirements. For example, NEC Table 310.15 provides ampacity ratings for conductors based on their size, insulation type, and ambient temperature. This table can be used to select the appropriate conductor size for the CT secondary wiring. In addition to the NEC, other industry standards such as ANSI, or American National Standards Institute, and IEEE, or Institute of Electrical and Electronics Engineers, provide guidelines for energy meter accuracy and performance. These standards specify the accuracy classes for energy meters and the test procedures for verifying compliance. When selecting an energy meter, consider the accuracy class and ensure it meets the requirements of the application. For example, a billing grade energy meter typically has a higher accuracy class than a sub-meter used for monitoring purposes. Furthermore, it is essential to understand the different types of energy meters available and their suitability for specific applications. Firstly, electromechanical meters. These meters use rotating discs and mechanical counters to measure energy consumption. They are relatively inexpensive but may not be as accurate as electronic meters. Secondly, electronic meters. These meters use electronic circuits to measure energy consumption. They are more accurate than electromechanical meters and can provide more detailed information about energy usage. Thirdly, smart meters. These meters are advanced electronic meters that can communicate with a utility company. They can provide real-time data on energy consumption and can be used for demand response programs. When selecting an energy meter, consider the type of electrical system, the load characteristics, and the communication requirements. In three-phase systems, it is important to use a three-phase energy meter to accurately measure the total energy consumption. For loads with high harmonic content, a true RMS meter should be used. If remote monitoring of energy consumption is required, a smart meter with communication capability should be selected. In summary, determining the multiplication factor for an energy meter from the CT ratio involves dividing the primary current by the secondary current. While this calculation provides a starting point, it is crucial to consult the meter's manufacturer for the most accurate factor. Additional considerations include proper CT sizing, wiring polarity, connection integrity, harmonic distortion, documentation, meter settings, calibration, safety precautions, grounding, ventilation, and compliance with relevant codes and standards. By carefully considering these factors, one can ensure accurate energy measurement and reliable operation of the electrical system.